Thank you.
Thank you very much, Jennifer. It's a great pleasure and great honor to be here. Indeed, I've been in this community for quite some time, and it's a real pleasure to see this machine learning and Kumbaya workshop that takes a big room today. I think it was much smaller, let's say 10 years ago. So that's very nice. Indeed, I moved to this company called Alkin. So one game for you is to guess what it means. I said to Jennifer, you have during the talk to guess it. I will not talk about it. You will just see the logo on the first page, and in the last page, just the link to be recruited there. Otherwise, I will not talk about that. But it's a company doing AI for precision medicine. So what I'm going to talk about today is a topic which I realize is not very original. Large language models, a la GPT if you wish, for proteins and DNA. It's a very humbling experience because I'm aware that probably many people in this room are better than me in that field. I've done more than me, but I'm going to try to share at least some of the work we've done, and importantly share with you, my own take on where it goes, where it could go, what we could do with that in the near future. So just to give some context, even though it may not be completely needed, you're aware that other fields, in particular natural language processing, has seen some dramatic change in recent years with the use of these transformer-based language models. There are different ways to present what is a language model, but my own way would be maybe the picture on the left of this slide to say it's a machine that can read some text and produce some text in response to what it reads. Something a bit specific in the way it works is that it goes through mapping the input text to some numerical representation. Sometimes it's called the embedding. So this is what the transformer does. A transformer is a way to start from a text and map the text to numbers, fixed dimension. And from this, fixed dimensional representation of the text, which is supposed to contain, in a sense, the meaning of the text or the meaning of the instruction, if it's an instruction, to then be able, from this representation, to generate new text. The way the text is generated, it varies. It's typically autoregressive, but it all amounts to extracting from the continuous representation the sufficient information to be able to generate some text. And what caught the community and many companies by surprise is how good this simple ID can become, especially if it is trained on large corpora, large data sets of texts. Probably you're aware that it's when I say trained, it means that it's just trained by reading text. It's not supervised. So as soon as you have a large corpus of unannotated text, then you can optimize the parameters of how the text is represented and how it's able to generate new text. And there are endless applications today showing that these models are able to do a variety of tasks, including translation, summarization, text generation, etc. And it's been observed that basically that the bigger the training set used to train a model, the better the performance on many of these tasks, if you are able to train them, meaning if you have big computers and big access to big data. So this is more or less, in 2 minutes, how I summarize the current trend in NLP. Obviously, there is a big competition these days to say, well, let's train an even bigger model because it will be better, or let's be a bit smarter and try a smaller model, but in a smart way to make them competitive. What I'm going to discuss today is, no surprise in this conference, is how this should or can impact our field of biology. And in particular, probably the most obvious application would be to say there's tons of text in biology. When you take DNA or proteins, these are molecules, but it's easy to represent them at least as sequences of building blocks, nucleotides or amino acids. And so it's tempting to say, well, let's just follow the same recipe. If we collect enough DNA or protein sequences, maybe we can just pre-train a language model that will capture, something about proteins and DNA, probably the biological constraints which are present thanks to evolution. And so by capturing this, maybe it's a way to represent any protein or any DNA string in a continuous space, so that from there, we could be able to generate new ones, just like GPT, but maybe we can do other things like predicting functions or structures of biomolecules, like doing some search of homology, like doing classification, etc., etc. Of course, this idea is good, and it's easy to have. There's been tons of work. Here I just present a snapshot of high-impact publications that were published in the last few years. I think the most important publication is the one called "And Many More." So I apologize if your publication is not there. I think it just goes until mostly 2021, and already it was just a snapshot. The last months and couple of years, I've seen a tremendous effort by us, this community, to adapt to train models on these biomolecules in general, and look at a variety of very high impact applications. Okay, so I will not review all this work. What I will do is be a bit, more focused on things that I did with my colleagues and friends. And so I will tell basically two stories and then discuss the future. So the two stories, the first one will be about how these IDs or language models for proteins in particular can be used to improve how we detect homology between proteins and how we can align proteins. The second topic will be extension of these IDs to DNA, and I will present some project we did when I was at Google with PacBio on improving the way PacBio sequencing is done. I mean, not the machine, but the raw data processing in order to have better quality sequences out of the sequencing machine. And finally, depending on time, I will open some questions for the future. All right, so the first work is really protein alignment and homology detection, which is one of the oldest questions and topics that has been discussed even in ISMB before ISMB existed. The root of bioinformatics is really about looking at these DNA and protein sequences and saying, well, we need to develop algorithms to analyze them. Something that is well known is that when you take proteins, typically from different organisms, or even within some organisms, proteins of the same family, then just by looking at the sequences, it's possible using computational approaches to recognize that some families probably had some common ancestors. We call that homologs. And based on collecting a collection of proteins that share common ancestors, it's possible to do what we call alignment, meaning to recognize which amino acid in each protein corresponds to which one in some other ones. We know that through evolution, you have the sequences evolve by insertion, deletion, mutations. And we know that if we're able to collect, by sequencing to collect protein sequences, and we're able to align them to other ones, then it's very useful for a variety of tasks, including guessing the structure or the function of a protein. Like if you do metagenomics, you may collect new proteins and you want to know what they do. The best way is then to compare them to, in your databases, to proteins with known functions. And if there's match, you could say, well, probably the function is the same. It's very useful for phylogeny. We had many examples during SARS-CoV-2. Once you have the raw sequences, to reconstruct the phylogenies between different species allows you to understand the evolution. And it's also useful if you're able to align, to identify that some positions, for example, are very conserved, and therefore they are likely to be important because evolution decided they should never be mutated. Other ones are less conserved. So being able to align is a way as well to understand at the position level the importance of different positions. So it's important, and the thing is that alignment is not easy. And for example, these are two proteins, chemokines, which one from gorilla and one from mallard. So for people like me who don't speak English very well, a mallard is a duck, wild duck, right? So you take a duck and a gorilla, there are two proteins. These two proteins are in the PFAM-seed database, meaning we know their structure, and human experts, have analyzed the structures in that they really overlap, and therefore they're considered to be homologs, meaning probably there are some common ancestor. But once they are aligned using the structure, so when we have the good information to know how they align, we have this alignment. And this alignment, so this is how we present alignments. You have the two sequences and you overlap, so letter by letter, which letter is supposed to be facing which other. What we see here is that in green, you have a few positions which are conserved. So these are meaning it's the same letter in the same amino acid in the two proteins. But you see that most of the sequences is not conserved. So this is a case of remote homology, where we are in the range of 10% of conserved residues. And this is what is hard to capture. Like if I just gave you the two sequences at the top and asked you Do you believe or not these are homologs? And if yes, are you able to align them so that, for example, in this 3D structure, you are able to map each amino acid to the other one, which is in the same 3D position? Then in this case, the current technology doesn't work. This is a first surprise of PowerPoint. So imagine that this is an alignment of a current state-of-the-art aligner, so Smith-Waterman alignment, on which we tested 1,000 different configurations to make sure we pick the best one. And basically, it doesn't manage to align a single correct position. What's interesting is that it's hard to see here, but because the slide has been shifted a bit, but it manages to find an alignment with more conserved position than the true one, except they're not correct, right? So we are really in the zone where it's very hard from a purely computational approach to make the difference between one alignment that could happen because there are many conserved positions and the true one, which is even less good as the true one when you take the standard way to assess what is a good alignment. Right, so that's a case where current alignment doesn't work. And you may say, well, probably I've cherry-picked it because I need to give a talk. But when you take, if you do metagenomics in a new environment and you sequence DNA, you construct putative proteins. Depending on the environment, it's estimated that between 20 and 80% of the proteins that you find cannot be aligned to anything known, right? So it's not really cherry-picked. If you pick a random sequence in a random environment, probably you don't know how to align it. So there is a huge need if we manage, to go a bit deeper in how to align remote homologs. So a question is, since LLMs maybe will solve all problems, could LLMs solve this one? That's a tempting PhD thesis, if you wish, or research project. The question is, how would an LLM help you do that? Actually, to be a bit more rational, in principle, probably it's possible to do something, because when you think of what LLMs can do, I briefly showed many papers, but in particular, one important paper is AlphaFold and the subsequent papers that show that more or less using deep neural networks, including LLMs, from a sequence, it's possible to capture lots of information about the structure. And here you see that the sequence-to-sequence alignment, I'd say is hard. It would be much easier if we knew the structure. So naively, you could say, well, if an LLM from a sequence knows how to represent, capture information about the 3D structure, then maybe it could be able to also capture what is a good alignment between two sequences, because it captures more information than the current aligners that we use. So this is what we try to do, and I will explain now a bit the technique that we developed in order to use LLMs in order to learn to align proteins. And to do that, I will just start with what exists today. So when you are given two sequences and someone asks you, can you perform an alignment and can you score the alignment to know if the proteins are homologs or not? There are some variants, but more or less all the methods boil down to some alignment methods summarized here. Most of you have seen that. I will not spend time on that, but think on the left table, you have one sequence which is vertical and the horizontal. You build this matrix of scores that basically gives a score if you decide to align one letter of sequence 1 to one letter of sequence 2. For example, here on this table, every time you have an A against an A, you get 4 points. If you have an A against a G, you have 1 point, etc., etc. So this is like, parameters that have to be decided beforehand to run this table. And then once you have this table that shows you all the possible scores you can get by aligning every position of first sequence to every position of second one, the algorithm that is implemented is the one that finds the best path, so the best alignment that maximizes more or less the sum of the scores. Okay, and the magic, or the magic for all the students that take this course is that even though you optimize over an exponential number of alignments, you can implement it in quadratic time. It's called dynamic programming, and these are the equations. Okay, but so I just mentioned that to insist on the fact that finding the alignment is solved by this dynamic programming algorithm, but the alignment itself depends a lot on which numbers you put in this matrix, the 1, the 4, like someone decided that it's 4 for A versus A. If you change it to 5, you get a different alignment. So how to choose these parameters has been one of the questions in bioinformatics since the 80s. There has been many ideas, based on probabilistic models of evolution, based on optimization, etc., etc. And what we propose to do in this work is basically to say, well, maybe the LLM can help us learn what is a good score, meaning for every 2 sequences, maybe we could be able, using LLMs, to build a scoring matrix that would be well adapted to the 2 sequences. Because, for example, instead of saying it's an A versus an A, an LLM could say, well, this A in this context has this property, this A on this other context has this property, therefore they could be matched or not. So we will use more or less LLMs to design the matrix, and then we will use standard algorithm to find the alignment. Okay, so we will keep the good old, as Jennifer was saying, good old Smith-Waterman algorithm, but see if LLMs can be used to better set the parameters. And so this is what we did, and this is joint work with a great team at Google, actually, with Felipe Linares, Quentin Berthet, Mathieu Blondel, and Olivier Teboul. And so in one picture, this is what we designed. So here the goal, as I said, is a model to align 2 sequences. So if you take this small picture, I'm sorry for the size, here it illustrates how you would align a protein with 4 amino acids to one with 6 amino acids. It goes in several steps. The first step on the left is going from sequences to some continuous representation. So this is what I said the LLM, language models are doing. They start from a text and they represent it as vectors. So if you do that, in fact, with a sequence of amino acids, this thing is called a transformer. It's the good old transformer in deep learning. So this thing has many parameters, but once the parameters are tuned, they transform a sequence of letters into a sequence of vectors of a fixed dimension. Hence, I plot them in this matrix where each row would be the embedding of one letter, and there are many rows, one row for each of the characters in the input string. So this means that after the first transformers, the 2 sequences are mapped to 2 sequences of vectors. And there, from these 2 sequences of vectors, this is where we have a module, which I call P beta here, P like parameters. So this is a very, I will explain what it is, but a model that given every vector of the first sequence and every vector of the second sequence computes a score. And the score will be put in the scoring matrix, which is the 3rd stage here. So in fact, I didn't insist on that, we have 3 matrices of scores, one for mutation, one for gap opening, and one for gap extension. So all these parameters, instead of being fixed by someone, like when you use BLAST, you choose what they are, here they are computed from the 2 sequences, but still we create these matrices, and then we apply Smith-Waterman, the good old algorithm, to create some alignment. Okay, so the contribution here of deep learning is only in how we create these scoring matrices, and then we apply Smith-Waterman. Okay, so that's the idea, but that's the idea once the model is trained. As I said, there are many parameters both in the transformer and in this module that creates scoring from vector representations. The way in order to tune this parameter, we follow the machine learning approach, which is to say, well, let's collect data. So this could be supervised, unsupervised. I will explain exactly what the objective function is. But basically, we tune the parameters by backpropagation, like any deep learning model. And here there is a specific complexity here, which is that if you go back to the top, when I say you go from sequences to continuous numbers to alignment, the alignment is discrete, right? It's something. And if you change a little bit a single parameter of your model, it's likely that the final alignment will not change, right? Because it's a discrete thing. So if you change a lot of the parameters, the best alignment would change, but it's, let's call that piecewise constant in terms of how it depends on the parameters. So this is the bad news for gradient-based optimization, because it does not, it breaks the backpropagation of gradient. It means there is no gradient of how better your alignment can be if you change a bit each parameter. So in order to train this, we needed to do something more, which is not only use a Smith-Waterman algorithm that produces an alignment, but to create something that we call a differentiable Smith-Waterman algorithm that, instead of providing a unique alignment, provides, call that a continuous alignment, with the property that the continuous alignment at the end is a continuous and differentiable function of all parameters, right? And so this is what allows to compute a gradient of how good your final alignment is versus a ground truth alignment if you have it, and to update the parameters during training in order to train your neural network. Okay, so there are two ideas in this slide. One is the architecture of the model, and two is the need to create some differentiable version of alignment if you want to be able to train it by gradient descent. Okay, so let me give, for those of you who are experts better than me in LLMs, just to give you quickly the ugly details of what's behind everything. The first is just a plain transformer. Actually, we borrowed exactly the architecture of the model called ESM, published by Reeves and Hall in PNAS. It's, compared to GPT, it's a very small model, but it's one that was well adapted, let's say, to the size of the training set we had. So for people familiar with transformers, there are 6 layers, and we map. So what this does is to map every position in the sequence to a vector of 768 dimensions, right? This is the mission of this block, transformer block. The thing important for those of you not familiar with these models is that the representation of every letter, like the R in the 3rd position here, depends not only on the fact that it's an R, but depends on the whole sequence, right? This is really the strength of this model, to say you have a sequence of amino acids, and at the beginning, this amino acid is itself, but after a few layers, it incorporates the information about the surrounding amino acids in order to run a representation which would be different from twice the same letter at 2 different positions, for example. So this is how this is why at the end, in the scoring matrix, it will not be just a score between A and A. It will really be a score between A in this position in this sequence and A in this position in that sequence. Every time you change the position of the sequence, the scoring would change. The second part, I said, is how we transform a sequence of vectors into a matrix where for each vector versus each vector you have a score. Here we didn't do much. We started with just saying, let's take the inner product. It's a way when you have 2 vectors, you do some inner product, you get a score. That could be a candidate thing. After a few experiments, we found that instead of the plain inner product, it was beneficial to be slightly more complicated. So we created what's called a bilinear function. Think of it as a weighted inner product. So we optimize the weights of the inner product. And this is the module that, given every embedding in dimension 700 of each position of the first sequence and the second one, computes this score by doing some weighted inner product between both. I simplify a bit. The last part I said is once you have the scoring matrix, I explained earlier how you can find the best alignment, dynamic programming, and you get it. But the result is piecewise constant, so it's not possible to compute how the output of this varies smoothly as a function of the parameters. So we created this differentiable alignment, which in itself, is something that we and others have found to be successful. The important thing to mention here is that this is a relaxation of the Smith-Waterman. So it's a bit, we have a parameter where you can tune it to become Smith-Waterman, but if you tune the parameters, it becomes less Smith-Waterman and finds a continuous alignment. And again, the main reason to have that is to be able to compute gradients, how the output depends on the inputs, and to use that to optimize the parameters. If you want to know more how this is done, I won't have time to detail it here. I'm happy to discuss and take questions later. But suffice it to say, for those of you who are a bit in this field, that there are basically 2 ways that we explored. One is to replace some max operation by softmax operations. Remember that in Smith-Waterman, you have a max of 3 things. If you are doing your networks, you know that you have many softmax functions that can replace the max. So that's one way to do, and you can prove that when you do that, you end up with something that behaves like a relaxation of Smith-Waterman. Another way that we found a bit more efficient, actually, is to use a technique called differentiation by perturbation. So here is based on defining an alignment as some mathematical expectation of many alignments under some distribution, and to randomly sample these alignments, which fits well the notion of stochastic gradient. So I won't go deeper there, but on the right part, which is perturbed, we literally only use the raw Smith-Waterman. The way it works is that every time we want to compute a gradient, we add some noise in the parameters of the model. So it will create an alignment at the end, which is not the same if you do it twice. So it's a stochastic alignment, but it's good enough to compute a gradient to optimize the model. If you want to know more, again, there are some references here, and I'm happy to discuss that offline. So at the end of the day, we have this model that can be trained. So we have this succession of models, embedding of sequences to sequences of vectors, then computing of parameters, then computing of alignment. And we can confront that if we have examples with a ground truth alignment, like, for example, obtained from 3D structures. We can confront the prediction to the true one, define a loss function, and backpropagate the error to the parameters so that after training, the predicted alignment gets closer to the ground truth. And so this is what we implemented in DDAL. And I must say that as is usual in these types of model, the objective function that we picked is not only training supervised by alignment, but we mix this with what's called the standard language model loss function. So, because transformer is a language model, we also use the same language model as ESM or GPT, which is how good the model is at predicting the next amino acid, as well as the task of homology, where we said, well, here we compute an alignment, plus we have a score of these alignments, but we want the score of true homologs to be larger than the score of non-homologous sequences. So we also gave examples of pairs which you should not be able to align. So, when you align, you always find an alignment, but then you need to decide if the sequences should be aligned or not. So we also use this knowledge of some sequences are known to be homologous, some are not to be homologous, to define a loss function that discriminates between true homologs and no homologs. And we combine the three loss functions together to finally train this model. So does it work? Well, I decided to cherry pick one example earlier, the gorilla and duck proteins to be aligned. I said that if you take any existing aligner with standard substitution matrices, you will never be able to align them. At least we tried with 1,000 examples. Here, the DDAL model makes it almost perfectly. So I must say the DDAL model was not trained on this sequence. This is one example where the model was trained on different families, and we tested it on this example. And this just shows that basically DDAL is not perfect. I think F1 is 0.94, because if you look closely between the top two sequences are the true alignment, and the last one is predicted by DDAL. You see it's almost the same, but there are a couple of positions which are not the same. So it's not perfect, but you see at least it finds overall it finds in particular exactly what are the conserved residues. And these are important residues. And if you look at the 3D structure, the cysteines are very important there. They stabilize the structure, and DDAL probably relies on this information to anchor the alignment on them more than the rest, and then manages to fill the gaps. We did evaluate a bit more systematically, if DDAL is good at, for example, discriminating homologous versus non-homologous sequences. On this plot, the vertical axis is some performance in terms of AUC, and horizontally, it's a level of difficulty of the task. And remember that the task of alignment is easy if the two sequences are very similar, and it gets harder if the two sequences are, share very little sequence similarity. So horizontally, you have the sequence similarity, and you see that if it's above even 20%, the two curves, so the green and orange one, which is orange is DDAL, and green is the best alignment with the substitution matrix that we found, they're almost perfect, right? So there is no need for new things. But as soon as you're below 20%, like in the 10% or below range, then the performance really degrades. So this is what I call, my cherry-picked example, which is probably the majority in many metagenomics data sets. And we have, depending on the difficulty, the DDAL improves compared to the existing models by increasing AUC from something like 70% to above 90%, so significant jump. And if you look at the quality of the alignment itself, it's less impressive, but still in the hard cases, we have F1 score going from something like 57 to 67, so 10% increase. So there is still a lot of work to be done, right? Don't take home the message that we have solved completely the remote homology detection and alignment problem. But I think this shows that there is at least some benefits to be gained there. And probably, we did something. We had to make many decisions in how we train the model, how we build the model. I'm sure there is still much room to be for improvement in this field. So I'll stop here for this part. If you want to try it, please give us feedback. It's available on GitHub. And so it's not a great, interface, but at least if you know how to type Python in a notebook, you can enter 2 sequences, run it, and get the alignment of the DAL, the alignment of standard aligners, and start playing with that. Okay, so I'll now move on to a second project, which you will see is related, and don't worry, it will be shorter. I'm seeing Jennifer worrying about the pace of progress in the talk. So this time, I insisted on proteins, but obviously, alignment is useful for proteins. It's also useful for DNA. Actually, when I was taking the example of ACGT, you could have guessed that it was not really a protein. So here I will discuss a bit about similar models, and in particular this differentiable alignment model, how we used it to solve a problem to do DNA sequencing. And so this project was done in collaboration with PacBio. If you're in sequencing, I'm sure you know about PacBio Hi-Fi sequencing. So this is a technology for long-read sequencing, which really produces reads of tens of thousands of base pairs. A difficulty with long reads is that they are, it's longer, but the error rate is higher than short read sequencing. And so what PacBio has designed as a technology, again, I super simplify it to try to summarize what's important for us, is that it sequences many times the same parts. So it's what's depicted on the right here. Imagine that you have a piece of DNA that you want to sequence. It's organized into a infinite circle that can be sequenced many times. And every time it's sequenced, there are a fair amount of errors. But you can imagine that if you sequence again and again the same sequence, then after a while, if you just average, you will converge to the true sequencing, to a true sequence, just because it has been shown that the errors in sequencing are not systematic, and so you can remove the noise by sequencing many times. So this is what exists, and it's been quite successful, actually. But it's not perfect. In particular, it has been shown that you need to really have many runs of sequencing again and again the same piece of DNA to have acceptable error rates. And so a question that we started working on, again, I was at Google at the time, was to say, can we use some LLMs or machine learning in order to improve not the technology itself, but how from the raw data we predict what is the true sequence. And again, as a baseline, I mean, you can imagine, I said, as a baseline, you have many sequences, so you more or less align them and average at every position what letter has been sequenced. PacBio at the time had a similar idea, a bit more evolved, based on hidden Markov models, which was really smart. That took into account the sequence sequenced by every time the machine was sequenced, plus some information about quality control, etc., to derive a consensus sequence. But I thought it was possible probably to improve this algorithm. So the question is, can we improve the algorithm so that the final sequence that you obtain when you use the sequencing machine has less errors? Because we know there are still errors. So I was part of a team so together with PacBio and a team at Google, where we worked on this project, and we at the end of the day we developed this model called Deep Consensus that was presented in Nature Biotech earlier this year, which basically is this model that takes the data coming from the sequencing machines and produces a sequence for each read. Okay, so of course the real algorithm or software has a number of steps. There is some raw processing of the signal to extract descriptors. Then there is a preparation of a consensus. Then you do that on many short pieces. Then they are stitched together. There is still a number of steps. But here we focus on a specific area, which is how from a description of what has been sequenced many times, you create a consensus. Okay, and so this is where, before this collaboration, PacBio was using some model based on graphical model, based on hidden Markov model, to summarize the collected information into a consensus sequence. And what we explored was instead to say, well, this can be maybe formulated just as a machine learning problem, where as input you have all the numbers and coefficients that you have captured while sequencing many times your reads. And as output, you have one sequence, which should be the good one. Okay, so we explored a model doing that. So input, output. You see it's slightly different from just consensus per column. We used a model very similar to a transformer model. So this is very similar to, it's a language model, if you wish. But in this case, everything was fitting together. There was only one difficulty, which is that, again, to train the model, we needed to compare the predicted consensus sequence with a true one. And it's well known that the types of errors that we were doing were mutations, insertions, deletions. So a natural way to compare if your prediction is good or not versus the correct one is to go through some alignment. And not only some alignment, so scoring some alignment, but as well being able to backpropagate a signal saying that your prediction is good because it's almost the correct one in terms of alignment distance. So here again, basically we reused and adapted but reused this idea of having a differentiable Smith-Waterman alignment to compare the candidate predicted by the model to the true sequence that they had to train this model. And thanks to that, we were able to train the model, optimize all parameters so that after optimization, the consensus sequence provided by the transformer was very close to the true sequence on the training set, up to some short alignment distance. So we implemented that, and going directly to some results, we found that it was, so this was really deeply investigated, not by me, but by the teams in PacBio and Google, to be sure it was correct. They came up with much better results in terms of errors. So this reduced by about 40% the number of errors that were found in the sequences produced by the algorithm. So keeping the same technology, just change the algorithm and you decrease your errors by 40%. That's always cool. This means you have less errors, or if you prefer to pay less, it means you could also do less sequencing for the same level of error. So it's a way to change a bit the balance between cost and accuracy. And in particular, so I won't go through all the details, but if you look at the bottom picture here, where you have 3 columns, the first column is the yellow one. So this is errors, right? If you're high, you're not very good. So the first one is the model they had before this project, so the HMM-based model. The second one, which is a bit better, is the transformer, but our first version that did not use the differentiable Smith-Waterman loss. So it was just predict a sequence, compare it to the true one from left to right, and without surprise, as soon as you have some insertion or deletion error, your way to measure error is not good anymore. But still, this improved a bit over the state of the art that they had. And when we moved to the differentiable Smith-Waterman loss in blue, then we had a very important decrease in errors. So it's really being able to compute a loss that was differentiable and that captured the types of errors that we are doing that made the difference here, that allowed us to train a model with good performance at the end. All right, so I now finish, with it's not research projects that I've done. I will just finish with a few comments that I think could drive questions for the future in the context of LLMs and maybe more generally what's called foundation models in biology. My first comment is, I've been myself working. I was at Google, so very involved in the core machine learning community. I think it's fair to say that us here in this room and those not in the room but involved in machine learning for CompBio. It's a big community, but it's a tiny drop compared to the massive community of engineers and smart researchers working on NLP, etc. So I think it's fair to say that so far we have mostly borrowed models, approaches, objective functions, way to do from NLP. It has been already quite successful. I presented just my work, but don't forget about the tens of other fantastic work that were presented here and published in the last few years. But I think to me, it's clear that there is room for new ideas and new things to be tried just because we did not. And I think this is something I heard many times, even here, people saying, well, we borrowed the model, we tried it, and it works, it's fantastic. I'm sure we can do even better if we spend the time to think a bit deeper about what are the good models, what are the good questions, what are the good way to process data, etc. So I will maybe discuss a few of these ideas. Sometimes there are very simple ideas like tokenization. For those of you who do NLP, it has been. I know the people at Google and OpenAI, etc., worked on that. This has been really studied. Millions of dollars invested in trying many things to converge to one way to do tokenization of English, Chinese, and French. I didn't see yet. Maybe I missed it, but I didn't see yet so much, time and money invested just thinking about the question: how do you tokenize, if you tokenize DNA or protein sequences? We did some work on that. I will just quickly share that, what we did. And I think in the community, there is some consensus after doing some basic investigations that, for example, K-mers is a good way to tokenize. I've been myself involved with a few students over the years. It's not trivial at all to decide if it's good or not, what K should be. We have found that the bigger K, the better. But then if K is too large, then it's not good either. So probably some adaptive K could be used. Some people have tried to borrow the tokenization of NLP, etc. So just want to say that to me, this is one of the simple but completely open questions for which, I'd be happy to get feedback from people more experts than me in this thing. But again, just set this example to show that these types of questions, believe me, in NLP, there's been really, really lots of experiments done to fine-tune and decide what is a good tokenizer for English. And we're not there yet in biology. I think there's the same question for architectures, neural networks. We're lucky that transformer, you borrow it from NLP, plug it to DNA, protein, and I can make a talk with 40% improvement. Maybe in 5 years, some people will say, well, look at the old guys like me, they just borrowed the transformer, but now we have the good architecture, and we still, again, gain 40%. I think there's tons to be discovered in that space as well. I'll just mention, to illustrate, again, one work that I did with a student about when you do a model for DNA, if you happen to care about double-stranded DNA, like suppose you want to make a model that predicts binding of a protein over the double-stranded DNA, there are in fact two ways to represent the double-stranded DNA, right? There are two sequences because you have two strains, so two sequences equal up to reverse complement. So you could say, well, what does that imply on my neural network? Like the neural network, when it sees one strand or the other, should do the same prediction because it's the same object, right? But if you don't specify it, there's no way your GPT will do the same prediction. It just sees two sequences. So you could just start from that and say, well, how can I change the model? Should I, and how can I change the model so that it's aware of these symmetries that exist? And for example, we've been working on this very specific question with Vincent Mallet. And for this very specific symmetry, again, we're able to characterize, actually there's been some work before us doing that by Anshul and others, but to characterize the space of architectures which can be used to preserve the reverse complement symmetry. So it's just a mathematical statement, right? This is a theorem that we had here. And then we implemented it and showed that if you are able to, if you decide to add this prior knowledge, so this symmetry in the architecture, then on a few benchmarks at least, you are able, with the same data, the same training procedure, but just a specific architecture to increase a bit the performance. So that's really what I mean by saying, we need collectively to spend more time and think a bit deeper about, once we have something that works more or less, can it be improved? Can we put more prior knowledge? Can we systematically assess the impact of design choices on the performance. And I think I'll finish by an open idea, which I mean it's not only mine. I think more or less many people are thinking about similar ideas, but there was a debate actually yesterday, a very good one, about foundation models in biology, with no consensus about the result, but at least many good ideas were shared. I think to me there's really something, because it's a keynote, maybe some of you came out of interest without knowing very well what are foundation models and LLMs. And well, you just mentioned that to me there is something very specific about the architectures that we use today, like the transformer that's used in language. It's a model that is able, to do two things to me. It's able to, from a series of building blocks, to learn a representation of these building blocks in the context of other ones. So like I was saying, when you say, protein sequence is a sequence of amino acids, the transformer builds a representation of each amino acid in the context of the other ones, right? So it's one way to capture interactions between building blocks, maybe communication between building blocks. And the second thing that does the transformer is that from the representation of all the building blocks in their context, they manage to represent the whole, right? Like a construct made of building blocks. This is how GPT, from a sequence of words, constructs not only a representation of every word in the context of the sentence, but as well the representation of the sentence itself, which is used to generate the answer. And so when you ask any biologist whether it's relevant in biology to have a model that captures multi-scale behaviors and interactions/communications between entities, I think the answer is a consensus. It's yes, this is, at least in biology, we can agree that these things are important. And so I believe there is really room for, probably in coming years, more and more of these foundation models that could be developed not only for single modalities, like for protein sequences or for single-cell transcriptomics or for digital pathology images, etc., but that they could be connected together, because every model is a way to go from one scale to the other. So from a representation of DNA to representation of cells, maybe to representation of tissues, maybe to representation of populations, etc. So that will be my 2 cents in this debate about is there a future for these models. I'm tempted to say yes, and I believe in particular, leveraging this capacity to model, so to capture interactions between building blocks and to go from one scale to the other is probably an idea that can lead us to a maybe more coherent way to represent, embed all sorts of biological data into a model that allows computation. I'll stop here. I think the conclusion is self-contained. Thank you all. And as I said, this is my only mention of how keen we're hiring. In particular, we want to develop these foundation models for biology. So if you care about that, please reach out to me. Thank you.
Thank you for a fabulous talk. Open it up for questions. Am I supposed to pull them? You come down here, I'm told. I don't have to move.
So thanks, this was great. My question is on the first part. So if you go to very remote homologies, I'm not a specialist of proteins, rather of DNA, but should we not even question whether things align at all and have actually alignment-free representations of the homology between proteins?
Yeah, so that's a very great question. I think in particular, sometimes you have convergent evolution of proteins that have no common ancestor but converge to the same structure or other mechanisms. So maybe I can just comment on what we did, what we define in our benchmark and to train the model as true homologs are the ones from the PFAM-seed database. So PFAM families, then curated by expert curators using 3D structure. So then, personally, probably they may be in the room or some other rooms. I'm not sure exactly if they have rigorous rules to decide, when the structure is similar, if we should call them homologs or not. I think so at least they call them homologs. But just say that our work follows this definition, right? The PFAM-seed one. Now I agree that to me, when I justified the model, I said that to me what can be captured by these LLMs is typically the function and structure, just like we use them to predict the 3D structure. So I'm not sure they are designed to capture whether there is a common ancestor very far away, whether we are at the boundary, but at least what I expect these models to do is to be able to align things if the 3D structure can be aligned. That would be my definition of remote homology here. And then to mimic, so to have the sequence alignment that mimics the 3D alignment.
All right, hi, thanks. I wonder about the following. So the way I understand it is you have ESM model.
Yep.
And on top of that, you do have this differentiable aligner, which you train on top of ESM. There is work on training directly on multiple sequence alignments, for instance, the MSA transformer. And I wonder what your intuition is about training directly with the loss, being aware of family, versus doing it sequentially in sort of like a downstream prediction type of approach, which I guess yours is more.
Can you be more accurate? What you mean by downstream?
So I view the second stage, let's say, fine-tuning of the model towards including homology or distant homology as sort of like a second step on the model rather than baking in a loss into the.
Yeah, so I mean, my answer would be, what I said at the end. We tried something. I think 100 people need to try, and maybe there will be some better ideas. So no claim that this is the best idea for sure. Now, maybe two comments. One is that, I said we borrow ESM. In fact, what we did is we just borrowed the architecture of ESM, but we retrained from scratch. And basically, we train all parameters simultaneously. So we will train this ESM, but with this additional loss function, meaning the embedding itself is slightly different from ESM. That's one. Then the question, should the input be a single sequence or some alignment? By design, what we want to do here is to have, so at test time, let's say, is not to have alignment, because the use of that is you have a new protein that you cannot align to anything. So we want to be able to align it to something. So by design, it cannot be in alignment. So to us, this was the justification to say, let's focus on a model that just takes one sequence versus another one. But there may be other ideas, maybe at train time, if you know that you have something maybe suboptimal in what we do is that, to extract examples of, let's say, true homologs that can be aligned, we start from PFAM, meaning we start from a multiple alignment. We have it. And what we do is we randomly take two sequences out of it and say, okay, this is one example of a 1 versus 1 alignment. So in the way we design the model, we start, in the training set, we start from multiple alignment from which we extract 1 versus 1 alignment to train the model. Maybe it's suboptimal, and maybe there may be fancy ways to say, you don't need to do that. You can just put the full alignment at train time and do something. I know there's been some work, so we tried, and others have published work on extending this work to predicting not 1 versus 1, but multiple alignment directly, right? If you have a collection of sequences, you say, I have 1,000 sequences from the same family. The output is the global alignment, input, output, and you can do it as well.
Yeah, I had a question. From what I understood, the Smith-Waterman algorithm is quite slow. And I wanted to know if that was a big bottleneck for the training, and if it was, how did you go around it?
Yeah, so indeed, in this, I think in this pipeline, this is the slowest part. So the way we did is that we implemented it in a completely parallel way. So others have worked on optimizing Smith-Waterman. So we tensorized it. We had to implement it in PyTorch and JAX. It was JAX in this case. But so yeah, we did spend some significant engineering work to accelerate it.
Okay,
and it's available. So this is, you can look at the code in the GitHub. Part of it is a fast Smith-Waterman.
Question? I'll ask him mine later.
Okay. So for the first part, in the alignment part, the variant affects data, like this mutation, this change is pathogenic, non-pathogenic. Do you think this, I mean, we use the alignments to do these predictions, but can we do the reverse, get this data to feed into the network to learn this context-specific mismatch scores? I mean, could it help, maybe?
That's a good idea. I didn't think about that. So yeah, I think in principle, I suppose there are many ways to do, but one way, so yeah, we have to think about that. So what you say is that some sequences belong to one category, pathogenic, others do not. So I can imagine that, in the spirit of deep learning models, you can just take the same architecture and add some model that from the embedding predicts the pathogenicity, and that could be a forced loss function that you jointly optimize, so that you run an embedding that is not only able to capture homology and language modeling, but as well predicting different functions. That could be one way to do it.
Thank you so much.